So welcome, everyone. I am delighted to see you here. I'm Ann Curzan, Dean of the College of Literature, Science, and the Arts, and I'm here to introduce Stephen T. Cundiff, the Harrison M. Randall Collegiate Professor of Physics. While we wish that we could hear from and celebrate Professor Cundiff in person, and we look forward to when we're able to do that, today's lecture is being streamed live to maintain social distancing. We do have closed captioning today, so please click the CC button at the bottom if you would like to access the closed captioning. And we will do a Q&A at the end, and so if you have questions during the lecture or afterward, please use the Q&A button at the bottom and you can submit the questions and I'll be moderating the Q&A. So collegiate professorships are named at the discretion of their recipients to honor an esteemed member of the faculty, a colleague, or peer. Professor Cundiff chose Harrison M. Randall as namesake of this professorship to recognize his many contributions to U of M's Department of Physics. And I do want to say the collegiate professorship is the highest honor that the college bestows on its own faculty. Harrison McAllister Randall was born in Burr Oak, Michigan in 1870. He attended U of M, where he received 3 degrees, all in physics. He wrote his PhD thesis on the coefficient of expansion of quartz. Known as precision metrology, his discipline was also the physics department focus in 1902, the year that he joined the faculty here. That changed after his sabbatical in 1910 at the University of Tübingen in Germany. He was introduced to infrared spectroscopy by his mentor, Friedrich Paschen, which influenced Professor Randall to shift his field of study, as well as the department's field of study, to atomic, nuclear, and theoretical physics. Further distinguishing the department here at U of M, he recruited top physicists like Otto Laporte and David Denison to the faculty. He also drew superstars like Niels Bohr and Enrico Fermi to U of M when he established the Michigan Summer Symposia in theoretical physics. In the 1930s, he raised money to build what was then the world's largest cyclotron. After 22 years as chair, and for anyone in the room who's been a chair, just think about that, 22 years as chair, he retired in 1941, just after the East Physics Building was renamed Randall Laboratory in his honor. Professor Randall died in 1969 at the age of 98. Professor Stephen Cundiff has been called a pioneer, and here I quote, the best of his generation, who leads in ultra-fast semiconductor spectroscopy. He studies the optical properties of materials and the generation and manipulation of ultra-short optical pulses. And in a few minutes, he'll discuss his renowned work developing optical frequency combs based on mode-locked lasers. Stephen Cundiff studied under Professor Duncan Steele at the University of Michigan. He was among the first to receive his PhD in applied physics and the very first to complete both master's and PhD in the discipline at U of M. He held 2 postdoctoral fellowships, including at Bell Laboratories. And in 1997, he joined JILA, a joint institute between the National Institute of Standards and Technology, NIST, and the University of Colorado. During this time, he was also chief of the NIST Quantum Physics Division. And then in 2015, much to our benefit, he came to the University of Michigan, but not without other offers, prompting a peer to write, quote, he would be a great catch. I can only encourage you to try hard to get him. Professor Cundiff's research has been funded by top federal entities, including the Army Research Office, the Department of Energy, and the National Science Foundation. It has also led to a body of published work, impressive in volume and critical reception. His early papers with Professor Steele, for example, have been called classics that create, quote, an understanding of a range of new phenomena in semiconductor optics. Highly cited, he has published nearly 220 journal articles alone, and his work has garnered him hundreds of invitations to present at conferences around the world. An engaged instructor, he enjoys teaching at all levels, from honors introductory physics to upper level optics courses. He has advised nearly 60 postdoctoral, PhD, and master's students and 24 undergraduates, yet he still finds time to serve on committees across the department and the college. And just recently, he did terrific work on a committee focused on faculty governance here in the college while he was in the middle of applying for a huge NSF grant. And I'm very grateful for that. Professor Cundiff's been called, quote, an extraordinarily good citizen with an exceptional record of service to the Optical Society, the American Physical Society, and other top organizations in the field. In 2017, he was named a fellow of the American Association for the Advancement of Science. Among his numerous honors are the American Physical Society's Schawlow Prize in Laser Science, a Humboldt Research Award, and the Optical Society's William F. Meggers Award. Praised for his, and here again I quote, intellectual leadership, superior research excellence, and broadly collaborative work, a colleague predicted Professor Cundiff would bring unmatched benefits to the physics department. We at the College of Literature, Science, and the Arts fully agree and find it most fitting that Professor Stephen Cundiff has been named the Harrison M. Randall Collegiate Professor of Physics. Please join me virtually in congratulating Professor Cundiff on his many achievements. And so now we imagine applause. And now, Professor Cundiff, if I can I call you Steve?
Sure.
So we actually have a surprise for you. And so I am going to disappear here for a moment, or at least Professor David Gerdes, who is chair of the physics department, is going to join us because we have, thank you, there is Professor Gerdes. I'm going to turn things over to him.
Okay, thank you, Dean Curzan. Steve, in naming your collegiate professorship, you could not have picked a person of greater significance to the Department of Physics and to LSA than Harrison Randall. And you heard from Dean Curzan about Harrison's many accomplishments, of which I have to say, serving 22 years as chair is a record that I am certain will never be broken. But for all those accomplishments, first of all, Randall was a brilliant, a diligent, a hardworking scientist who spent many hours in his laboratory in the building that now bears his name. And so if you will allow me, I'm going to share my screen and show you a picture. This is Harrison Randall in the newly constructed, what was then called the Physical Science Building in 1925, in what looks like the sub basement with what looks like a spectrograph. And I want you to notice that he's sitting down, and that will be important. The equipment that he accumulated in his laboratory over the years, of course, took on his personality and his character, and it was still there when our colleague Jens Zorn arrived in Ann Arbor as a new assistant professor in 1962. He was given the laboratory space that had belonged to Randall himself, and I'm sure he got rid of a lot of stuff that he inherited in there, but the lab contained one prized possession that Professor Zorn kept and used himself for most of his own 47 years on our active faculty. That object was Harrison Randall's wooden laboratory stool with its legs cut down to fit Randall personally. And there it is. So Steve, as we inaugurate your Harrison M. Randall Collegiate Professorship, it is Professor Zorn's wish that we present you with this stool as a token of our admiration and respect for your work, and as a reminder of the heritage that you and your group are continuing to build on right there in that same building. Thank you so much, Jens, for this wonderful and thoughtful gesture. So congratulations, Steve, and enjoy your very own collegiate chair.
Thank you, David, and thank you, Jens.
Great, thank you, David. This was a nice surprise in the middle of this. And Steve, before I turn it over to you for your lecture, we've started a new tradition, which I really love, which is I get to ask you a couple of questions. And the first is, how did you discover your field? How did you land here?
So I actually started working in optics as an undergrad, but in a probably an unusual fashion. I took a job as an engineering aide at a small company, and ended up staying with that company and indeed not going to grad school right away. I took 2 years off in between undergrad and grad and was working. And there I started working on both spectroscopy of things like rocket plumes, an interesting thing to do spectroscopy on, and also using lasers to monitor, well, to understand atmospheric fluctuations. So I became interested in optics in general, decided to go back to, ended up here at Michigan, and when I was looking for an advisor, walked into the office of Duncan Steele, mentioned that I had read a Scientific American article on phase conjugation and the spatula laser. And turns out he had done some similar work related to that at Hughes Research Labs, and that got us talking, and I ended up working with Duncan. And so that was the sequence that got me there. And ever since, it's just been an evolution.
So thank you. I love these stories of, it goes back to, you know, I walked into someone's office, had a conversation, and that was an important part of your career. And then my second question is, as in terms of your research, what do you find to be the most rewarding part of it? What gets you out of bed in the morning?
So I think there's two things. One is just the sort of the thrill of scientific discovery, of waking up and thinking about a problem and thinking about whether or not I have a new way of approaching it, or we have a new idea, something new to tackle. I also say, as a faculty member, I really enjoy watching graduate students grow. I sometimes, when they come to their thesis, I think about, I remember when this person walked in my office for the first time, and you know, the first conversation with them. And some of them, I've had several, including one who's going to graduate soon, who walked into my office as an undergraduate. And so I really got to see them go from being a very junior person to being somebody who is now ready to be an independent scientist.
I love it. And I am sure we have some of those students here with us today for your lectures. So Steve, I'm really looking forward to this, and I am going to turn the floor over to you.
Thank you. So I want to tell you today about, let me get a laser pointer here. As Dean Curzan said, about my work over the last 20 plus years on optical frequency combs. So first, let me ask you a question, is what is an optical frequency comb? Now I realize I'm not in a lecture hall, so I can't ask you to raise your hand, but this is the day of Zoom. So we're gonna pop up a Zoom poll and allow you to choose which one of these four options you think is a frequency comb. Julie, can you pop it up? Okay, how many votes do I, apparently this was already available to you is what I understood. So people have already voted. Looks like most people have voted. Okay, can you, oh, this is the results already, I got it, okay. So good, I'm glad to see that. Most of you were able to eliminate two of them, okay, which is the first and the third, which are clearly there as something to make you smile. And most of you got the right answer, which is the bottom one. Often when people think about frequency combs in my field, they think it's simply a spectrum with equally spaced narrow lines. It turns out that is insufficient. Although a frequency comb will display such a spectrum, it actually needs to be to display mutual coherence between the different waves. And I will come back to you at the end to try to reinforce this point. So this is the correct answer. So it turns out the frequency combs have a close tie between not just the frequency domain picture, but the time domain picture. So let me start with that. So if we have a train of pulses here, so that's what this top shows. This is a function of time here, that are separated by a time. I'm going to call it 1 over the repetition rate, f rep. And each pulse has a duration delta tau. If we look at the spectrum of that, so the spectrum is the underlying sine waves that when added up give you this pulse train. For your eye, those are the different colors that would come together to give a color you see. Or for your ear, that's all the different frequencies or the different tones that come up to make a sound you hear. But in the frequency domain, you're going to have this broad distribution of frequencies where the width is given by 1 over the duration of the pulse. So this is a classic Fourier relationship. It actually underlies the Heisenberg uncertainty principle in quantum mechanics. But if we look very closely with very high resolution, we'll discover that there's this series of very sharp lines, very discrete tones that are separated by the repetition rate. So 1 over the time between the pulses, okay? Now, as I mentioned, lasers are often used to produce these pulse trains or these frequency combs, depending on how you want to look at it. So what I'm going to do now is just briefly describe how a laser works. So a laser stands for light amplification by stimulated emission of radiation. So that means we have something we call a gain medium. It amplifies light. Light comes in stronger than it went in. And we need to bounce the light back and forth to create feedback. And we do that with mirrors. The light bounces between the mirrors, as I show here. A little bit of it leaks out one of the mirrors, and that is the laser beam that comes out of a laser you're used to seeing, right? So one mirror we call a high reflector. One is an output coupler because the reflectivity less than 100%. And the pair of mirrors make up what we call a cavity. Now, it turns out a critical thing is again, this light wave bouncing back and forth is actually a sine wave. And it must actually come back to be in phase with itself after a round trip, otherwise it would cancel. And so that requirement means there's only certain wavelengths which have an integer number of wavelengths per round trip. It's given by this formula here. It's just the length of the cavity divided by an integer. If we convert that to frequency, it's a set of discrete frequencies, which is the speed of light divided by twice the cavity length, again, times an integer. So only these very specific frequencies are in this output, right? Now, as I said, we want to think about a train of pulses, and we want actually quite short pulses. And so you might ask, how do we make a short pulse with a laser like this? And you might say, well, why don't we simply turn it on and off? Maybe stick something in it to block it or turn this gain off. The problem is that on this time scale, actually the speed of light is pretty slow, and it matters because if we turned it off, we'd have to wait for all this light to make a round trip in the cavity and escape out this output coupler. And of course, not all of it escapes, so it actually take quite a while, many circulations before that happens. The speed of light may look like a fast number to you, but on the length scales we're talking about, we want to think here, so it's about 30 centimeters per nanosecond. And so it would take many nanoseconds for this to happen, and the pulses we want to make are actually much shorter than that. They're actually on the order of less than a picosecond. That's 11 zeros followed by a 1 after the decimal place. And so we can't do it by simply turning this laser on and off. Instead, we do it by optical interference. So this is a simple animation. Here is one of those modes in a laser cavity. The output is completely continuous, nothing like a pulse. If we now have two of these, there's one more wavelength in this top one, you'll see they interfere with each other. They beat against each other just like the beat in tuning a piano or a violin. If we add a third one, you see that this beat region is getting shorter, and a fourth one is getting shorter. So the more of these modes we have adding together, the shorter the pulse we get. If we have many, this shows you 30, we get a quite short pulse. Again, you actually see it oscillating in the cavity here. However, a key thing is that they're all in phase. This is what we call mode locking. If they weren't in phase, we just have noisy output as it's shown here. So I'm not going to tell you how we get lasers to mode lock, but we do. And we get them to make these trains of short pulses as I show you here. So what I just showed you is actually sort of going the other way, starting from this sequence of discrete pulses here, discrete modes rather, discrete frequencies, and showing that when we simply add them up, we actually end up getting this pulse train in time. Now, if all the pulses were identical, as I've shown you here in this sketch, actually that would mean that these discrete modes, these discrete frequencies, are simply integers times this repetition rate. And all lasers would actually generate good frequency combs. And so the whole field of frequency combs would have started with the laser itself back in the 1960s, rather than starting in the 1990s. And the important thing is that they're not all the same. So let me explain to you why they're not the same. And they're not the same because of something called the carrier envelope phase. It's sometimes called the absolute pulse phase. And the point is generally in optics, this overall phase doesn't matter. As I mentioned, in optics, we often measure intensity, okay, just the intensity of the light, which it has to do with just the height of the sine wave, not the actual phase of the sine wave. And usually it's only a relative phase between two different light waves that matters. But when we have these very short light pulses, which are on the order of a few cycles, so this is a femtosecond, 10 to the minus 15 seconds, we can actually now reference this wave off of the peak of the actual pulse itself. So that gives us a new reference. And the question is, when does this phase of the light wave with respect to the pulse itself actually matter? I want to note, as I said, often people call this an absolute phase. There's no reference for the clock itself that we're clocking it off. So in that sense, it's not absolute if you're being very careful about it. But if you use the pulse itself as a reference frame, it becomes an absolute phase. A key problem is that the phases actually evolve. And this is due to the fact there's two different velocities. The pulse travels at what's called the group velocity, whereas the underlying light wave travels at what's called the phase velocity. And in most materials that have what's dispersion, so that means the different wavelengths travel at a different speed, those two are different. And so you get this evolving pulse as I show you in this animation. And the point is, inside a laser, we always have this dispersion and we need to take it into account. So when you take it into account, again, this simple animation shows that. Here we see our pulse evolving inside the laser, and you see the phase is evolving, but we basically record the phase every time the pulse comes out. So you see these two successive pulses in the pulse train have different overall phases, and we need to take that into account when we determine what the pulse spectrum looks like. I'm not going to go through the math here. It's actually not hard to do that. I'm just going to tell you the answer, which is that if we now include this, you see here is a pulse train where the pulses now are, where I'm really showing you the full electric field. The pulse phase is evolving from pulse to pulse. And if we now take the Fourier analysis of this, that tells us what the spectrum looks like. We still have this very broad spectrum here, which is the spectrum of a single pulse, this broad envelope. Okay, it's 1 over the duration. We still have these sharp lines here, okay, and they're still separated by by the repetition rate, okay, but they are not simply integer multiples, they're offset by this amount we call the offset frequency. So the frequency of any comb line, so we often use the Greek letter nu for the frequency, optical frequencies, nu sub n is the integer n times the repetition rate plus the offset frequency, where the offset frequency is given by this relationship here, and it relates back to this pulse-to-pulse shift in the carrier envelope phase. Now that may seem a little bit abstract to you, a mathematical sort of analysis that gave it to you, but I'm going to try to prove to you that you can actually appreciate this directly by using your built-in acoustic spectrometers, otherwise known as your ears. And what I'm going to do is I'm going to play for you, if the gods of Zoom will be with me today, a acoustic pulse train. So the pulses are at 100 hertz. The carrier wave is at 4 kilohertz. And this first pulse train I'm going to play for you has all of the pulses in phase. So this delta phi equals 0. So I hope you can hear that. It should be playing through Zoom for you. And now I'm going to play another pulse train where the pulse-to-pulse phase shift is 180 degrees. They're basically flipping with each other, okay? Now, people who are excellent musicians and tell me that they have perfect pitch say they can hear the difference. I'll also warn you that if you're listening on headphones, you may not be able to hear the difference because the low frequencies are critical. And the low frequencies often don't come through in headphones very well. So if you're on computer speakers, it's probably better. So if you're on headphones, you might want to unplug them for the next one. In the next one, what I'm going to do is the first half of this clip will be the pulses in phase, and halfway through, it's going to switch to the pulses being out of phase. And you should be able to hear the transition. Oops, wait a minute. So if you have good audio, you should have heard the frequency go down a little bit as that offset frequency shifted from being 0 to being 50 hertz, and the whole comb moved over a little bit. So hopefully that convinced you that this is a real effect, and what we're looking at is this effect for light, not for sound. All right, so I want to make one more point, which is the distinction between optics and electronics. And so you might ask, why are you even talking about this? Well, fundamentally, from a physicist's point of view, there really is no difference. There's a set of equations called Maxwell's equations that work equally well for electronics and optics. But from your real world experience, you think they're quite different from each other. When you think of optics, you think of things like microscopes, telescopes, or even like my eyeglasses. Whereas when you think of electronics, you think of a circuit board, a bunch of wires all hacked together like that, right? So what are the distinctions? Well, this shows you one distinction, that in optics, typically the wavelength is much smaller than the component size. So the wavelength of light is about a micron. Obviously, these are centimeter scale objects. Whereas in electronics, the wavelength is actually typically maybe, say, tens of centimeters is a typical signal that you might have inside your computer, the wavelength of that. For old-fashioned radios, it's even much longer than that. But the component sizes are much smaller. So that's one difference. The other one is one I've already mentioned, which is in optics, we typically just measure intensity, whereas in electronics, it's easy to actually directly measure the electric field. And so it actually turns out to be an important problem and quite useful to figure out how to merge these two. And so one example of that is measuring the absolute frequency of light. So what does absolute mean? Remember, I used to work for NIST, which is the National Metrology Institute for the United States. So to measure something absolutely means you must reference it to the relative definition. And for a frequency, that definition is the second. And of course, the second was originally based on the rotation of the Earth. It was 1 day divided by 86,400. The Earth is actually a really poor standard. It's slowly slowing down, and also it actually fluctuates a good bit. So today we don't do that. Instead, we use what we call a quantum standard, which is that it's roughly 9 billion oscillations of the transition frequency between two hyperfine transitions of 133 cesium. Okay, so this definition was agreed upon in 1967. Now note this number here, sorry, let me get a laser pointer back again, is 9 gigahertz. So that is a radio frequency, and we want to measure light against the radio frequency. So we need to connect these. More broadly, if we can connect these, we can use the methods from one regime and the other. And so specifically, for example, coherent techniques, which are easy in electronics, they rely on measuring relative phases, have been challenging in optics, but learning to connect those makes it easier. So how do frequency combs help? Well, the point is that these pulse train coming out of lasers here, the time between these pulses might be the order of a nanosecond. That's a frequency of 1 gigahertz. So that's an electronic frequency, but it's overlaid on this carrier wave, as we call it. Okay, so the product are these. And that carrier frequency is an optical frequency. And so if we can lock these two together, we can lock the time between pulses to the actual underlying oscillation of the light wave, we've made a direct connection between them. In this sense, we call the laser in this case is a frequency divider. It's dividing the optical frequencies down to the radio frequencies. But I've sketched this here with this pulse-to-pulse phase shift, so we do need to take that into account, and it's critical that we know about and measure that pulse-to-pulse phase shift. So in optical frequency metrology, what we need to do is determine that, and we developed a technique back in 2000 in this paper, where we could do it with a technique we called self-referencing. I'm not going to go into the details of self-referencing here, but I do want to comment a critical step in self-referencing is second harmonic generation. And of course, optical second harmonic generation was first demonstrated by Peter Franken here at University of Michigan in Randall Labs. So once we have this self-referencing technique working, we know the offset frequency through the self-referencing. It's actually quite easy to measure the repetition rate. You just take the output of the laser and you put it on an ordinary photodetector, and the electrical signal that comes out is at the repetition rate. And so we now can reference both of these to a cesium clock. Again, these will be radio frequencies. It's easy to make that comparison. And we now know the absolute optical frequencies referenced to the primary standard of all of these. It's broad. We can measure many different frequencies. I'll come back to that. And what we have is some unknown laser, which is typically a narrow single frequency laser. We measure a beat note between that and a close by comb line. We measure 3 radio frequencies, and we can measure we can know what the frequency of this unknown laser is. So why was that important? Well, we need to think about how this was done before frequency combs were done. And it was done using something called a frequency chain. So for example, we start here at about 9 gigahertz with a cesium clock. You multiply it up using things like a klystron. So this is what's in your microwave oven to make microwaves. You actually get up to lasers. These are actually working on a molecule, an alcohol, up to CO2. And you do multiple steps, and eventually you get in, for example, to one of these lasers in the visible, and you can measure it. This is really hard. This is a diagram of probably the best frequency chain ever built at the Physiktechnische Bundesanstalt in Braunschweig, Germany. There are 12 separate oscillators here. It starts again from the cesium standard and gets to a calcium frequency standard. So in this case, this experiment, I actually saw it. It was in 3 separate rooms at the PTB and required about 5 PhDs to keep it running to make a single measurement. At the end of the day, they measured a single frequency. So this is like building a ruler that measures the distance from Ann Arbor to Detroit, but you have to build a whole new ruler to measure the distance from Ann Arbor to Lansing. Not a good way to do things. And it was very hard to make these measurements. Frequency combs solved this problem, as I described on the previous view graph. You made simply 3 measurements. Indeed, a second-year grad student could do it. I actually have proof of that. I had a second-year grad student back in Colorado who made such a measurement. And moreover, you could actually measure many, many lasers all at the same time. My colleague, Jan Hall, had several of these highly stabilized lasers in his lab at Jilla, an iodine stabilized laser, a rubidium stabilized laser, and he just measured them all right away once we got this frequency comb technology working. This sort of gives you an idea of that. So this is a graph put together by my former colleague, Leo Holberg, looking at the uncertainty in optical frequency measurement. So in this case, down is good. A smaller uncertainty means you made a better measurement. This first one was made by Ken Evenson back in 1973 as part of the project for redefining the meter. And you can see they were coming every few years. This is infrared, optical is harder. The uncertainty was going down slowly. But you can see something happened around here, and that was the introduction of femtosecond frequency combs. And so you can see that the uncertainty plunged. The number of measurements went up significantly. Indeed, it continued to grow. The uncertainty is now below this. It's down at about the 10 to the minus 17 level. But what I want to point out is something interesting happened right here with this last point in about 2005, which is if you look at the uncertainty of the primary standard, the cesium microwave clock, the optical measurements actually exceeded that. So what do you do when your measurement is better than your standard, okay? How do you actually make a better measurement? What you do, okay, let me give you an example, which is the speed of light. So these are measurements of the speed of light. This first one was made by Michelson back in the 1880s. This one was actually made by Jan Hall in conjunction with his measurement by Ken Evenson. And at this point, this measurement uncertainty was better than our current standards. It was no longer a platinum iridium bar, but still it was better than the best measurement. So what did they do? They redefined the meter in terms of the speed of light. So that means the uncertainty went to 0. So indeed, that's what's happening today. The measurement community, the metrology community is talking about redefining the second, not in terms of a cesium transition, but in terms of optical transitions. It's breathtaking how good these clocks are. Indeed, general relativity has always been a significant effect in the clock community. So when NIST Boulder at 1800 meters reported the time on its clock to Paris, to the BIPM, where they keep track of universal coordinated time, they always had to put in a general relativity shift. Now these clocks are so good, you actually have to put in a general relativity shift if you compare 2 clocks that are on different floors in the same building. And indeed, the fluctuations in the local gravitational potential will probably become an important part of the uncertainty. So this has been about optical atomic clocks, optical frequency metrology, certainly a fascinating topic to a narrow group of people. I have to say that optical clock or atomic clocks do matter for everyday people because it's the basis of GPS. But can combs have a broader impact? And so the answer is yes. And I want to introduce another comb-based technique, which is dual comb spectroscopy, where we take 2 of these mode lock lasers that have a slightly different repetition rate. So this animation is working for you. You'll see these pulses are slowly drifting through each other. So this pair is roughly in phase and then are synchronized and they slowly drift out. And so what's happening, these pulses are sweeping through each other, and we can use that to map real time into delay time. And so this has been around for a while. It was known as asynchronous optical sampling. And the big advantage is you could get these pulses to scan through each other much more quickly than if you use a traditional technique, such as a actual mechanical moving delay line. It was first described for combs by Ronald Holsworth's group over in Germany. And in this case, that overall phase of the pulses becomes important. And it's actually easier, again, to go to the frequency picture, where now we have, again, this sequence of comb lines, but again, they slowly drift apart. We take these two frequency combs and we combine them. We see a beat on a photodetector. And so when you look at the spectrum of the electrical signal, we again see a comb, which is now separated by the difference in repetition rates. But we can map these comb lines back to the optical frequency. So we can say that this comb line corresponds to this optical comb line and so forth. And so if one of these lasers goes through a sample that absorbs, so say a molecular molecular sample that's absorbing certain colors, so you see this comb is reduced here, that comes out in this radio frequency comb. And so we can actually make a direct mapping and we can see the absorption spectrum. And again, the advantages are that this can be done very rapidly, okay? It can be done with a relatively compact apparatus, and it can be done with high resolution that's hard to use with traditional techniques. And so this has actually enabled a lot of real world applications. Again, this is an example of this where they had a frequency comb in a building. They bounced it off a retroreflector on a drone and measured the absorption in the intervening path, right? So for example, more recently, they've shown that they can monitor methane emissions from oil wells by using a similar technique where they take one of these systems out to an oil field. However, this is still limited because this is actually a pretty complicated apparatus, although it's not quite as sensitive as, for example, one of those atomic clocks. For the oil field work, they actually had a custom van that they had all this back in the back of, and they were shooting the laser beam out the back of the van. So it'd be nice to come up with a more compact, more efficient, energy efficient, and less expensive approach. And so my group has been working on this recently here at Michigan. And so we've demonstrated that we can actually use a diode laser. So a diode laser is the kind of laser, for example, in a laser pointer or in your CD player at home. This is a homemade diode laser here. That's actually it right there for scale. This is a 0.5 centimeter section of a ruler. So the actual device is only a few hundred microns long. And what we do is we design it to make these combs, and we go through here. This is a hydrogen cyanide cell. And the sharp red lines are the combs and the comb lines, and the blue is actually the spectrum of that. So we're seeing absorption peak. So each one of these is a peak where this hydrogen cyanide molecule absorbs. So this is a much more compact device, and actually it can be run on batteries. So this is a battery pack that we run it on. So you can imagine that with these devices, you could even have these frequency combs, for example, built into your cell phone and actually be able to locally monitor atmospheric absorption, or you can make small compact devices that you could scatter around and they'd be quite inexpensive and frequency efficient. So in the last couple of view graphs here, I want to mention another thing we've been working on. So one of the challenges of this kind of spectroscopy, so if we go back to this one, we see these absorption peaks here. We happen to know, in this case, we have hydrogen cyanide in there. So we assign them to them. However, if we have a mixture, this actually becomes very difficult. We don't know necessarily how to assign the absorption peaks. We'd like to use them to identify what's in the mixture. However, if it's an unknown mixture, this can be challenging. It'd be hard to figure out what the different components are. So to address that, people have developed a technique called multidimensional coherent spectroscopy, which actually spreads this in 2 dimensions. We do this by using 3 combs, so we call it tricomb spectroscopy. So 2 of the combs go through a sample. They actually generate a new signal, which we then detect using the same dual comb technique that I was talking about with this local oscillator comb on a single photodiode. This shows a spectrum. As an example, we used a rubidium vapor. This is the hyperfine spectrum of rubidium. But the key thing here is that this is actually the highest world record resolution for this optical multidimensional coherent spectroscopy. So this is our result down here. This is spectral resolution, down is good. But if we had done this spectral resolution using typical techniques, so these are the more traditional techniques that use some kind of mechanical delay stage. In this case, it uses crossing beams. But the point is, if you take these green lines and extrapolate them down, they would have taken basically hundreds of minutes or even days in order to achieve this resolution. And so we did it both with high resolution and with very short acquisition time. So let me finish by returning to this question of coherence and what it means for these comb lines to be mutually coherent. So coherence is something you hear about when you hear that a laser is coherent, unlike a light bulb. And so coherence means that if we have a nice sinusoidal signal like I've sketched here, if we know the phase of it at one place in time or space, so I'm thinking now this is time going from left to right, but it could actually be space. It could be a wave front, the phase of a wave front. But if we know the phase here, we can tell what the phase is over here. And if it's a perfect sine wave, that works. We measure the phase and we can say what it will be at some arbitrary time later. But it's easy to have something in there that causes the frequency of this to fluctuate. So in a laser, for example, if those two mirrors move a little bit, it actually causes the frequency of that mode to change and the frequency of the sine wave it emits to change as well. And if that happens, we accumulate a phase error. So you'll see here in this sine wave, the frequency here is actually the same as the frequency here. So there's no difference in the frequencies, but the phase is shifted because transiently the frequency was different. So typically these events are random or stochastic. So that means that actually these phases become stochastic and we no longer have coherence. So in this case, the blue sine wave is actually losing coherence with respect to itself earlier. Mutual coherence means we can have two signals. In this case, these two signals have different frequencies, but they're both mutually coherent and they're mutually coherent, which means that if we know the phase of one of them and we know the relationship, we can actually predict the phase of the other one at a later time. Now, if we have one of those fluctuations, if it's the same in both of those, we can actually use the phase evolution of one of these, even though it's no longer fully mutual coherence, to determine the phase evolution of this one. And so we get the phase later. And this is critical because, for example, in the dual comb spectroscopy, we often track the phase of one of those comb lines and use it to correct the phase of the others. It was also critical in the optical frequency metrology because it's this phase linking across different frequencies that, for example, allow us to break down this barrier between electronics and optics. We can now make phase coherent measurements over a very broad range. So let me finish with a quick summary. So coherent optical frequency combs have revolutionized absolute optical frequency metrology. Indeed, this is no longer a field of active research. It's a done deal. You can buy a system to do it for you. It's enabled optical frequency synthesis, and it's enabled optical atomic clocks. Dual comb spectroscopy, I believe, will have a broader societal impact. So for example, I mentioned atmospheric monitoring of both greenhouse gases like methane, also looking for pollutants and so forth, other pollutants. And advances that we've been working on are promising to make dual comb spectroscopy ubiquitous. So the diode lasers will allow it to happen in a small, compact, and efficient way. And also the techniques are trying to make it more powerful. Acknowledge that many people have worked with me over the years. I didn't want to put a huge list of names. I'll just highlight my group. This is a group picture from several years ago here in Randall Lab. A lot of them have now moved on in life. This was sadly a group picture from last fall when we had to take a group picture on Zoom. So with that, I'm happy to, I'm done. I'm happy to take any questions.
Great, thank you so much. And I'm not going to pretend that I understood all of that because it's been a while since I took my last physics course, but really fascinating to the applications that you're talking about and the work you've done to make these more, as you say, ubiquitous, efficient to do this work. So I would encourage those of you who are experts in the field to use the Q&A button, welcome questions, and I will moderate those. And I'll start with this question, which is, what do you see as the thorniest problem that you and your team are now trying to work on?
Well, One is not science, which is the ubiquitous problem of raising money to keep on doing research. So, but as far as technical problems, as far as, for example, the diode combs, we're still learning how to control them. So they work well for this dual comb, but we would like to actually use them for some other applications. The physics underlying a diode laser is very different than the physics underlying a typical laser. And so we're still trying to understand that, how we would actually get the exquisite control we can get over some other types of lasers. I'll just say for the other topic I mentioned there at the end of the trichome spectroscopy, we demonstrated that using a atomic vapor, which is actually a great sample because we know exactly what its spectrum should look like, but not particularly interesting for the applications. So we're actually working on trying to extend this into the infrared region, what's called the fingerprint region. We're actually working with a local company that makes these fiber lasers that work at those wavelengths. So we're trying to figure out how to implement some of these ideas in those wavelength regions using a different set of lasers.
Mm-hmm. And I love it that you started with the first one, which is getting the grants to do the work. So we have this question that's come in. What are the ultimate limits to metrology?
Okay, so the answer to that is always quantum mechanics. So, you know, for example, you run into quantum limits for basically everything you can measure. And this is actually a quite interesting question with regards to frequency combs. When I first started talking about frequency combs, I was and a friend, a gentleman by the name of Moreau, he was actually still at Michigan at the time, of course, the Nobel laureate in 2018, professor here, stuck his hand up and asked, well, you talk about this frequency, something about what's called the shallow Towns limit for a CW laser, which is a quantum, how narrow the frequency line. And why doesn't it apply here? And it should really blur everything out. So that actually sent me thinking about this for about 5 or 6 years, working with some theorists on it and determining that quantum limit, but it was actually quite different than the quantum limit that we developed the theory of that. Right now, the quantum limit for these combs is much, much below other limits. And so the people, for example, trying to do atomic clocks, they're actually running into issues with the interactions between the atoms. Even though they work very hard to reduce them, they still show up. And so the emphasis in that field is actually the physics of whatever the standard is. And that's what's limiting it right now. Now, ultimately, in some of these, you will run into things even more profound quantum limits as well. But that's right now, it is just the physics of the standard use.
And I love this next question that's come in. What advice would you give to new training physicists graduate students? And I'm going to ask you to do it in one would be about the field, and another would be about being a grad student. Advice that you would have.
You mean advice about what field to go into, or?
Well, I mean, this is what advice would you give to new training physicists? So let's come at it in a couple ways.
Yeah, there's a couple. So one thing is I would say to make sure that you choose a topic that you are really fascinated by. I mean, that what I like saying, and I say this to my friends sometimes, is, you know, I enjoy my work and therefore it's not work. You know, if you like what you're doing, it's no longer work. And so, you know, it makes sure, you know, if you really love tweaking knobs, then find a project that's tweaking knobs. If you like doing, you know, theory, then make sure you do that. The other thing I would say is choose your advisor well. I think that the relationship between a student and an advisor is probably the most important thing for how the graduate career goes. And you know, I think know people that it's been a great experience. I know people who've really not had a great experience, and I think that's probably the most important thing. So yeah, make sure it's somebody that you get along with and treats their students well, and you know, so I think that's an important thing.
No, I love that. I often say, you know, what are the questions that keep you up at night, that you think about, you know, that you really want to work on for years?
Right.
Because you're going to work on these questions for years. So
exactly.
You should, and that often people are like, oh, better be, maybe not that question, it should be a different one. So are there applications of these methods to the problems of gravitational wave astronomy?
So potentially, and I know exactly where that's coming from. I told you that the local gravitational potential will shift these clocks, and getting to the point where you can imagine that, and potentially they could be sensitive to a gravitational wave. The challenge is actually interesting. The challenge is actually communicating the phase information and the precision of that timing between the two clocks. So to do gravitational wave astronomy with these, you would need two clocks that are physically separated. And you would ask the question, do their tick rates change? And do they change? How do they change with respect to each other as the gravitational waves sweeps through? And I think the answer is right now, the clocks are actually probably on the edge of being good enough to do that. But what is challenging is then having that time transfer. And so this is a long-standing problem of doing time transfer at these very accurate levels. And so the truth of the matter is, I think so of course, for the experts, LIGO is the way you do a spectroscopy now. I think if you were to actually try to do this, you might end up with something that kind of looks like LIGO, which is you would need evacuated tubes with a laser beam going down it in order to actually be able to communicate the timing information without corrupting it.
All right, we've got another question here. When speaking about laser cavities with gaining media, why did you use the speed of light as it is defined in a vacuum? That is V equals C to N equals 1. Is the index of refraction the same as it is in the vacuum or negligibly different for all lasers with gaining media?
So I use the speed of light in vacuum just because that's what everybody knows. And that answer is a good question. Is a good question because indeed it is not the speed of light in vacuum. It is the speed of light in the material. For many lasers, you may have a relatively small amount of material. But an important point that question gets to is you cannot build a laser without having some material in the cavity. And the fact that you have some material in the cavity means you always have some dispersion. Every material has an index of refraction that changes. That's why, for example, glass spreads out the rainbow, the spectrum into a rainbow. And that means that you will always have this carrier envelope phase shift. It's not quite what the question was going for, but it's actually an important point. But indeed, yes, I was trying to be quick. And so I just use the speed of light in vacuum. Really, we should include the index of refraction. And it varies. For example, semiconductor laser, the index of refraction is quite high. So it makes a big difference.
And so let me ask you another question. And I'll use your language of sort of something that is now a done deal that probably 5 or 10 years ago we couldn't have imagined would be a done deal. So now I'm going to ask you to predict something that right now people are working on that you think 5 to 10 years ago, 5 from 10 years from now will be a done deal.
So I think that there may be some shifts in the way people measure spectra. Okay, so typically the way you do it, the standard inexpensive way to do it is the same way that Randall did it, which is using gratings. So a diffraction grating disperses light in different directions. And then you basically use that. That's not, laser spectroscopy does it in certain cases with a much higher resolution, but still, if you just go by what's called an optical spectrum analyzer, there are Fourier versions of it, but a lot of them still use gratings. I think that there's a good chance that some of these comb techniques are going to get to the point where they'll start to take over. And so we'll use them, and we actually have ideas where we might be able to replace a standing grating spectrometer with something that's based on comb techniques. And if they do, they could actually become less expensive and more compact. An interesting point here is that signal analysis is critical. And so it's not just the optics part, but it's actually evolution in some electronics that would allow that to happen as well.
So, and I'm looking to see if anyone else has a question. I'm watching the Q&A. Give people another moment. And Steve, let me ask you one other question. When you teach undergrads, what's one of those moments where you see light bulbs go off, where suddenly in what you teach, people understand or see the world in a different way?
It depends on what level you mean. So like in the optics course I teach, there's actually some sort of basic things that I feel like they've learned about, but don't actually know what the impact really is. And so there's cases there. So as simple as something of what's called a wave plate. And so often it's taught in a very sort of fundamental level, but then you ask them, and I learned this the hard way by asking the question, like, how would you use this to generate this kind of light? And it turns out they couldn't answer it. And I said, well, wait a minute, I never taught them that. So I realized next year, okay, I better not just tell them what this thing is, I better tell them how you use it. So I think when I taught honors introductory physics, which was a lot of fun, I taught it out of sequence. And so it was a small class, they're very dedicated students. There were a number of cases there where I don't know if I can pinpoint one anymore, but you could really see them sort of begin to put all the pieces together and understand how these things came together.
Mm-hmm. So I was in a meeting this morning where faculty were sharing those moments of, something that you teach where you see people suddenly come to a new understanding of something, which is always fun. So thank you so much. I'm now going to disappear from the Zoom screen for just a moment, because were we in person, I would present this to you in person, but I will present it to you. It's like the stool. So we have this lovely poster with this really beautiful image, which I know that you had produced, and which we saw on the journal cover. But we will get this to you as a way to remember this really terrific occasion. And thank you again for the lecture. Thank you to everyone who joined us today. And we're just appreciate all that you bring so glad you came and joined us in 2015 and all that you bring to the college and the university. So thank you so much for today. And again, I will ask everyone to virtually applaud. And I hope everyone has a peaceful evening, and congratulations again, Steve.
Thank you. Thank you to everybody for listening.